Until recently, our understanding of contemporary interstellar dust came from looking at it from very far away. Astronomers relied on remote spectroscopy, analyzing light passing through the glowing gas of the interstellar medium, combined with fleeting measurements from passing spacecraft. From this remote data, a consensus emerged. The community defined interstellar dust as uniform, dense particles measuring roughly 0.2 micrometers across. Theoretical models suggested that high-energy shock waves in the interstellar medium would rapidly amorphize any small silicates. Because of this, the canonical model assumed these dust grains were featureless spheres of amorphous glass, devoid of any crystalline structure. To test these assumptions, the Stardust Mission deployed a collector into the interstellar dust stream, captured physical particles, and returned them to Earth. The Interstellar Preliminary Examination Team then began the first direct laboratory autopsy of these samples. They identified 7 confirmed interstellar candidates. These particles immediately differed from the established astronomical consensus. They were larger, less dense, and possessed an internal geometry that the standard models did not predict. The particle named Orion contains a mixture of forsturitic olivine, magnesium spinel, and iron. Its X-ray diffraction pattern shows the distinct concentric rings of a preserved crystalline structure. By returning physical samples, Stardust proved that a complex, crystalline, large particle tail exists in the local interstellar medium, a population that had remained invisible to remote astronomical instruments. Finding these 7 particles required isolating true interstellar dust from intense local background noise. The Stardust collector used 2 distinct collection media, ultra-low-density silica aerogel and aluminum foil. The silica aerogel blocks absorb hypervelocity impacts. As a particle strikes the porous structure, it decelerates gradually, creating a deep track that traps the sample. Searching this material required a massive collective effort. A network of over 30,000 citizen scientists manually scanned millions of microscopic images of the aerogel for any signs of an impact. Every identified track underwent trajectory analysis. Particles bouncing off the spacecraft's solar panels strike the collector grid at predictable angles. Chemical analysis confirmed this, revealing cerium from the solar panel glass, proving the debris originated from the spacecraft. The SORIC track belongs to a subset called midnight tracks. These are impact features whose trajectories align with the incoming interstellar dust stream flowing from the direction of the constellation Ophiuchus. Trajectory modeling isolates a candidate pool, but chemical mapping provides the evidence needed to rule out local solar system debris. Interplanetary dust particles from local comets often share chemical signatures with interstellar dust because they form under similar physical conditions. To separate the two, researchers examined the aluminum foil. They used focused ion beam milling to reveal the microscopic cross-sections of the impact craters. Elemental maps of these craters showed distinct zoning, separating silicates, iron, and sulfides into different phases. Furthermore, a deep symmetrical crater points to a compact mass, while an irregular spread indicates a loose aggregate of nanoparticles. Oxygen isotope ratios often identify extrasolar material, but the contemporary interstellar medium's isotopic range overlaps with solar system values. Therefore, a solar-like ratio does not disqualify a particle from being interstellar. Instead, the team used the interplanetary micrometeoroid environment model to calculate the statistical probability of these impacts. The model shows that the likelihood of all 4 foil craters being uncorrelated local background debris is less than 0.16%. The combination of kinematic tracking, elemental mapping, and statistical modeling confirms that these particles originated outside our solar system. This evidence focuses attention on Orion and Hylabrooke. Both grains measure over 1 micrometer in diameter and weigh roughly 3 picograms, hundreds of times more massive than the canonical model predicted. Orion's elemental composition consists of a mixture of forsturitic olivine, magnesium spinel, and iron-bearing phases. This X-ray diffraction data from Orion confirms a complex, mosaicked crystalline structure. The concentric rings mapping to these tick marks demonstrate that the particle is not made of amorphous glass. This magnesium bicolor map of Hylabrooke shows a crystalline olivine core surrounded by a low-density, partially amorphized halo. These findings contradict the assumption that interstellar silicates should be entirely amorphous. Calculations suggested that shock waves in the diffuse intercloud medium would shatter and amorphize any crystalline structures over time. Because Orion and Hyalobrook are massive aggregates, their outer layers act as a shield against the intense shockwaves of the interstellar medium. These outer layers absorb the kinetic and radiation damage, preserving the crystalline material deep within the interior. These grains exist as complex surviving chimeras, carrying diverse mineral faces from distinct stellar environments into the local solar system. Before the samples were returned, models based on data from the Ulysses and Galileo probes predicted that interstellar particles would strike the collector at speeds exceeding 15 kilometers per second. This graph details the measured fluence. The Stardust collector recorded an order of magnitude fewer large particles than the models predicted. The solid black line shows the expected prediction, while the stepped lines below it represent the actual measured track density. The physical data revealed yet another discrepancy. The largest candidates, like Orion and Hyalobrook, impacted at speeds below 10 kilometers per second, much slower than predicted. The physical evidence contradicts the orbital models. This suggests that the established assumptions regarding the physical properties of the dust were missing a critical factor. Dust movement depends on beta, the ratio of outward solar radiation to inward gravity, a tug-of-war between light and mass. Theoretical models assumed compact grains. This low beta ratio means gravity overpowers radiation, pulling particles into the inner solar system at high speeds. But Stardust data proved grains like Orion and Hyalobrook are extremely porous, with densities as low as 0.3 grams per cubic centimeter. With this low density, the beta ratio increases. Solar radiation exerts more force, gaining leverage over the particle's trajectory. Solar radiation pressure acts as a massive physical barrier, decelerating these fluffy, low-density aggregates as they enter the solar system. This interaction explains both the low capture speeds and the low overall particle count recorded by the mission. The Stardust mission identified a fluffy, low-density tail within the interstellar distribution. Future models of the matter between the stars will need to account for these complex aggregates and their specific interactions with solar radiation.